Welcome to the polar forms of complex numbers. Recall the previous Cartesian complex number. So we have two solutions here, x1 and x2, represented by the real number and imaginary numbers. So you can plot that one in a Cartesian coordinate system. So that's why we can also call it Cartesian complex number or rectangular complex number. Okay? Because of the form of your number. So look at this for the first solution or first complex number x1. So you see a point there. Okay. Now if you make a line that coming from the origin, so you will find a radius or the length of the line, and then also the angle from the reference, which is the positive x direction. So from that you have two elements, the r and the theta. Okay, so basically you can convert that one, okay, by simply following this method. First, get the Pythagorean equivalent of the triangle. So you see you have this vector, and then you have the two components. You have the x and then the y. Sorry, that's, we can use the value directly. So we can use here -1, and then the other side is 2. Okay, then get the angle between them using the tangent theta. Okay, now you might wonder, why is it -63.43? Actually, the value of this angle here is somewhere 100. That's 114 or something. But you know that the angle, there are two possible answers. Okay, so actually this can be expressed also by 1. So 90 plus 24, so 114 or something. Okay, so it can be expressed to the positive side. Just simply add this one with 180, and still we get the same angle. Okay, so just follow this arctangent. Okay, and you don't need to worry about whether you need to add the 180 or not. Okay, so it can be represented like that. Okay, so if you just add 180, so these two angles are the same. Okay, because if you want to convert, for example, square root of 5 cosine -63.43, this is equal to square root of 5 cosine of, okay, cosine of 180 minus 63.43. Okay, so which is this one is the actual angle, but the two are the same. Okay, so in order for you um, not to get confused, so you don't need to worry about the angle here. Okay, whether you need to add 180 or not. Okay, because it can, the opposite angle here, okay, will give us the same result. Okay, okay, same angle. So let me erase this one. Okay, so you have this expression. Okay, square root of 5 angle -63.43. And then for the second solution or second complex number, we have that vector r2 with a theta 2, and then you can also use the Pythagorean equivalent of the triangle. So you have this vector here, and then you have the two components, -2 and -1. So you will get square root of 5, and then the angle here, actually the angle is looking at this portion. Okay, so but don't worry with this because that's here. Okay, actually the theta here, so the theta 2 here is the same as the theta 2 there. Okay, so this is basically a trigo. Okay, so but don't worry, just follow the angle arctangent of the y over x. Okay, so y is -2 and -1 is the denominator, so don't interchange the two, and then you will be safe regardless if this one is incorrect based on the graphing, but the two are equivalent, meaning this can actually be expressed like that, no? So you have this value here, and then with the angle theta 2, okay, or something, alpha, let's say alpha. Okay, so so this angle, because in trigo that there are two possible degrees that the trigonometric functions can be expressed. Okay, so in this case, we just simply do this because it's the easiest. Okay, so I don't want you to be complicated and be confused, so just do this. Okay, and then so we call the vector magnitude as the modulus and then the argument theta I. But for vector analysis, you can also use other terms like the magnitude, scalar value r, and then the angle theta or whatever. Okay, so basically the polar form is simply like this. Now you have a variable or the complex number z, and then you have the modulus r, and then the argument theta. So theta can be, there are two possible answers for theta. Okay, so I just repeated previously. So but you don't need to worry about it. Theta can be expressed as tangent inverse of y over x. Okay, and y is the imaginary coefficient. Don't include the imaginary I or j, so just the coefficient. In this case, we don't include the I. No, for example, here we don't include the I in the numerator, otherwise you will get a math error. Okay, it's just the coefficient, and then the denominator is the real value. Okay, so that's it, the polar form.